Welcome everybody to another physics class. In today's lesson, we are going to go ahead and do some sample problems for uniform circular motion. So these are some more additional problems. You have this worksheet available in Canvas, and we are going to go ahead and solve through it. As you look through these problems, some of these may seem hard or seem like as if there's no way to around them, but these are actually the easiest problems you'll ever get, not only in physics, but in any math class or even in standardized tests. These type of questions are what's called as logic questions. And when you see these without an actual number, remember that these are very easy to do. And I'm going to go ahead and show you how to take care of them. So let's go ahead and start with number one. A certain amount of centripetal force acts on a car around a curve. If the speed of the car was quadrupled, what would be the magnitude of the centripetal force? So the question is asking for us to find centripetal force. And what's changing here is the speed being quadrupled, or the tangent velocity being quadrupled. So notice that we don't have any kind of other numerical values, and these are the ones that you get to choose what it should be, or you select your own values. And this is what I mean by they are super easy as long as you follow a basic trick. So we know we're talking about centripetal force, and our equation for centripetal force is Fc is equal to mass times velocity squared divided by r. So that's our equation. And when you have a problem like this, you're always going to go ahead and set your original values as 1. So the trick to this is that set everything equal to 1 for the original value or the original scenario. So this is a certain amount of centripetal force. We don't know what that certain amount is, but we can go ahead and select that certain amount to be 1. And if we make our, I'm going to go ahead and write original here. So this is our original scenario. If we make the certain amount of centripetal force as 1, then the only way that this equation can make sense for one side to be 1 is for the other side to be as 1 as well. The only way you're going to achieve that is if every other variable is also 1. So the mass is going to be 1, the velocity is 1 squared, and that is divided by our radius, which is also 1. And if we write this out, 1 times 1 squared is still 1 divided by 1, so everything checks out. It's 1 is equal to 1. So based on these values, it makes sense that the centripetal force in this problem, or in any problem, that is, they don't give it to us, is equal to 1. So there's our original value. The centripetal force is equal to 1. Now what you're going to do is go ahead and take what the problem asks you to do and to simply go ahead and change that one single value. So we said that we're looking for centripetal force, which means that on the new one, or our second scenario, we're trying to find for centripetal force. So if we're solving for that one, we're going to go ahead and just write its variable. So we're going to say Fc instead of 1, because that's what we want to find out it is. So Fc. We're not going to change anything on our mass, so it's still 1. The speed or tangent velocity was originally a 1, but is now quadrupled, so that means that it's 4 times greater. So that's the speed itself is 4, the velocity is 4, but this gets to be squared, so 4 squared. And we're going to go ahead and divide that by still a value of 1 because there's no changes being made to our radius. So this was our speed that got quadrupled, the 4 over here. And we are solving for centripetal force. From there, you can just go ahead and punch it into the calculator. 1 times 4 squared. 4 squared is 16, so 1 times 16 is 16. 16 divided by 1 is still 16. So the centripetal force is 16. And it's a force, so you can say that is 16 newtons. Or you can say that is 16 times greater than the original force, because the original force was 1. So remember the Fc here would have been 1 newton. Or you could also say 16 Fc, 16 times the centripetal force, because we technically don't know what the actual value of that centripetal force is. So all of these are correct answers, as it is 16 newtons, or 16 times the original force, and 16 times greater than the original force. So that's number one, fairly easy when you start doing the trick. probably this would be your best bet of selecting an answer choice for it, because this would say that the new centripetal force is 16 times the original. All right, moving on to number 2. A test dummy is riding on a merry-go-round. Scientists are experimenting with different velocities. If the ride malfunctioned and the centripetal force was 9 times greater than the original setting, what happened to the velocity of the ride? So this time we're solving for the velocity of the ride. And what did change for us was the centripetal force. The centripetal force was 9 times greater. So again, this is a problem where they don't give us values, which means we are set to go ahead and select our own. Again, we're dealing with centripetal force. So our equation is still the same. Fc is equal to mass times velocity squared divided by r. I'm going to go ahead and write original. And since I've already done this once, I'm not going to go ahead and rewrite all of that. I know my original should be 1. So I'm going to go ahead and say that the centripetal force is equal to 1, or 1 Newton. And now I'm going to go ahead and go into my new problem, or new scenario. So for the new scenario, I'm searching for the velocity of the ride. So the VT, or the tangent velocity, is what I'm going to go ahead and write down when it comes to the variable. What we're changing this time was our 9 times, centripetal force was 9 times greater. So Fc was originally a 1, and this is going to become a 9. So this is 9 on the left-hand side, is equal to, nothing changes with the mass, so that's still a 1. The velocity is what we're solving for, so that's Vt, remember that's a squared, and only the velocity gets squared, nothing else, divided by our radius, which doesn't change, therefore it's still 1. And now we're going to go ahead and write these out. So 9, basically 1 times Vt squared divided by 1. If you want to get rid of the 1, you would have to multiply 1 on each side. And so this crosses out, this crosses out. You can multiply this by 1. So it's still 9 on this side. 1 times Vt squared, anything times 1 is still the same thing. So it is tangent velocity, or Vt squared, is equal to 9. The problem is asking for the tangent velocity and not the square root of, or the square of the tangent velocity. So you got to take the square root. So you got to make sure that you take the square root, which you do to one side, you also do to the other. These cancel out, and we get tangent velocity is equal to 3 meters per second. So the tangent velocity is 3 meters per second if the original one had 1 meters per second. So again, that's one way to write it. You could say that the tangent velocity is 3 times greater, or you could also say that it is 3 Vt, as in 3 times the original tangent velocity. All those would be correct. Okay, so now let's go on to a slightly different problem. In this scenario, they actually give us values, so these are not logic problems. This is an actual UCM problem in which we're going to go ahead and solve through. So it says that Danica drives a race car for a test run around a circular track of radius of 80 meters. She completes 7 laps in 4 minutes. Part A, what is Danica's period during her test run? And part B, what is Danica's average speed? So as we go through and try to go ahead and solve this, we need to make sure that we are writing down everything, but also paying attention to our units, as that's critical. So for part A, it says, what is Danica's period? And remember that period is, the variable for period is capital T. So for part A, I'm just going to write it over here. We've got capital T as what we're solving for, and that's a question mark. Now some of you may be thinking, well, the time is 4 minutes. That's the time. That is not the period. So capital T stands for period. Now, we're going to go ahead and write our different variables. Radius was 80, so r is equal to 80 meters. She has 7 laps, so the 7 laps, it's not exactly a variable, so you're just going to take that piece of info down. It's 7 laps, or you can think about it, since it's a circular track, 7 laps or 7 circles. And finally, our time was 4 minutes. Time, the variable for that is a lowercase t. So t is equal to 4 minutes. However, time always needs to be in seconds, and we can't keep it in minutes. So the t equals 4 minutes here needs to go ahead and get converted into seconds by multiplying by 60 seconds. So we get t is equal to 240 seconds. And now we finally have a time that is in the correct unit, and we can go ahead and proceed to find our period. Remember to never get confused the lowercase t with the uppercase T. This is time, that's period, and that's what we're trying to solve for. So if you watched the previous videos, you've noticed that there's two different ways to solve for period. The first one is using equation 42, and that is that, here's the first method, is period is equal to 1 over frequency, or 1 over f. Now, we did not have f over here. There's no way for us to find f, so we can't use that method right now. However, there's a second method, and that is when you're solving for period, you can use t is equal to the number of seconds over the number of revolutions. So the number of seconds over number of revolutions or circles. And in this case, we have t is equal to, our seconds was 240, and the number of circles or revolutions was 7 laps. So we divided by 7. So 240 divided by 7 gives us a value of t is equal to 34.92 seconds. The unit is still seconds. It is now a capital T for period. So this is our answer for part A. What this means is that it took her 34.92 seconds, pretty much on average, in order to complete one full circle. It took her 240 seconds to complete 7 laps around this track, but her period is 34.92 seconds to complete one circle, or one revolution, or one lap around this track. So don't get t time, lowercase t, and uppercase t as period confused. All right, so moving on. Now it's part B. It says, what is Danica's average speed? So for part B, we're solving for average speed. Now, even though this is a circular motion, and you might be thinking that that's tangent velocity, remember that tangent velocity is the straight line linear speed, and that's not what this problem is asking for us. So average speed is not tangent velocity. So average speed does not equal, and definitely is not the same thing as tangent velocity. So we're not going to be using that variable. Instead, we're going to have to rely on finding the total distance that she travels and divide that by the time. So we're going to go ahead and solve for this. Now, we do have a radius as 80 meters, but that's from edge of the circle or edge of the track to the center of this track or the circle. So that's 80. And you can't just think about the distance being 160, because that would be the diameter, and 160 is not the same as the distance around this. The distance around this circle would be considered the circumference of it. So in order to find the distance of this track, we are going to have to need to find the circumference of this track or circle. So circumference is c is equal to 2 pi times r. And we're going to go ahead and substitute our values. Circumference is equal to 2 pi times our radius of 80. So 2 times 80 is 160. C is equal to 160 pi. And once you punch that into your calculator, the circumference of this track is 502.65 meters. So C is equal to 502.65 meters. Now this is the circumference of this track, which means it is the distance that Danica travels in one single lap. If the question had asked us what is the total distance that she traveled, we would take this value and multiply it by 7, because she went 7 laps. And that would give us her total distance. However, the question saying for what is her average speed, Well, we know that this is the distance for one lap, and we also know that this is the time that it takes to complete one lap as well. So it goes back to V equals d over t, distance over time. In this case, this is our distance, this is our time for one lap. So we're going to go ahead and go back to V equals d over t, and I know this is referred to as linear. However, this is distance, and we know that her distance, and we've got a time that correlates with the circular distance as well. So that is going to be 502.65 divided by 34.92. Now I know you're seeing that this is a lowercase t, and I'm using the value for uppercase t. Remember that this stands for period, and this is the amount of time that it took one circle or one rotation around this track. So if we're using the distance for one lap around the track, which is the circumference, 502.65, we're also going to use how long it took us to complete that one single lap. So that's why we're using this. So we're going to go ahead and take 502.65 and divide that by 34.92, and it gives us our average speed or velocity is equal to 14.39 meters per second. Moving on to number 4. It says that ball 2 has a mass 4 times greater than ball 1. Both are moving in circles of equal radii at the same speed. So this goes back to a logic problem. They don't give us any exact values. We're free to choose. So we're going to go ahead and choose accordingly. It says, how do the net forces of the two balls compare to each other? So we're going to go ahead and compare the net force of ball number 1 to ball number 2. And before we do that, we can go ahead and we need to find what they are. Well, since this is a logic problem, remember that I said that everything that we do is for the original should be set to 1. So we are looking at, we've got mass and we have radius, and they're traveling at the same speed. So all of these are going to fall into our centripetal force equation. So it's still Fc is equal to mass times velocity squared divided by r. And remember that for the first one, everything's equal to 1. So if this is 1, mass is 1, velocity is 1, and the radius is also 1. So we get that 1 is equal to 1, and we get that the original scenario, Fc, is equal to 1 Newton. Now we can go ahead and solve for the second scenario with the second ball. And that one has a mass 4 times greater. So this is the one we're going to change, mass being 4 times greater. And we're solving for net force. Now I know this is net force and I wrote it as Fc. Remember that centripetal force is basically a net force. So we are going to go ahead and punch it in. We're solving for the net force here, which means that we are going to go ahead and write that same variable as we normally would. So this is centripetal force. This is for the new one. Centripetal force is what I'm solving for, is equal to the mass of this one is what gets changed. So the original was a 1, and that mass now becomes 4. So this is 4 instead of 1. And we have our velocities remains the same because it's the same speed. So still 1 squared, same radius, so still 1. So now you go ahead and write it down. Fc is equal to 4 times 1 squared. 1 squared is still 1, so 4 times 1 divided by 1, Fc is equal to 4 newtons. Since we're looking at a relationship between the two, you can say that the centripetal force of the original, or ball 1, is 1/4 of the ball 2, or you can say that ball 2 is 4 times the original of ball 1. So we could go ahead and say that so Fc for ball 2 is 4 times greater than Fc ball 1. Or another way that you could say it is that it is 4 times Fc. So that still works as well. So we could say that 4 Fc, 4 times the centripetal force of ball 2 compared to the original. So either one of these works. The relationship is that the second ball is 4 times greater, or that the first ball is 1/4 of the second scenario, the second ball. So there's another logic problem. And finally, our last logic problem. This is the same object as used in these scenarios. Which scenario has the least centripetal force? So we're looking for centripetal force, but we have to solve for basically ranking them in order from least to greatest before we can solve this problem. And it's hard to see, but these are all circles. You have the radius here and here. It's a bigger circle, so it's 2 times r. This one's a smaller circle, so it's r divided by 2. The velocities for these two are the same. This one is twice the velocity, and this one's twice the velocity. So there's 4 different circles. It's the same object in 4 different tracks, if you will, with different velocities and different radiuses, depending on the scenario. So we're going to go ahead again, set our original as 1. And by that I mean we could set the variable of r as 1 and set the variable of velocity as 1 as well. So it's nothing different. We're going to go ahead and do original. And our original, since that falls into this category of r and v that we're going to use as being 1, this is going to be our original, is essentially letter A. So the original is going to be essentially part A, or letter A, choice A, if you will. So this is A, this is B. We'll say that this is C and this is D. So original for this one, our centripetal force, we're going to have to set it to equal to 1. The only way this works is everything else is also equal to 1. Remember that it's mass times velocity squared divided by r. So it's 1 squared over 1. So for letter A, the Fc is equal to 1 Newton. For letter B, that's our new one. We're going to have to keep doing it for each one now. For letter B, r is still the same as what it was. However, we are twice the velocity. So we're solving for Fc. So Fc is our unknown. It's equal to, it's the same object, so the mass remains the same. What changes for this one is that it goes from 1 to 2, because it's twice the velocity of the original. And this is 2 squared. Radius is still r, so this would be 1. So Fc here for letter B would be 2 squared is 4. 4 times 1 divided by 1, it's 4 newtons. We're going to go ahead and do letter C, which is this one up here. Now for this one, the radius is twice as long, but the velocity is still v, so that velocity remains the same. What gets changed here is our radius value. So we're still solving for the Fc of this one. Mass is still the same object. Velocity is back to being the original v, so that's 1 squared. And the radius is now, instead of being a 1, it is twice that, so it's 2 times 1, so it's a 2. So the centripetal force for this scenario, for letter C, would be 1 divided by 2, or 1/2, or 0.5, however you want to write it, 1/2 newtons. And we're going to go ahead and do letter D. So letter D is this tiny small one. This is the radius is divided by 2, so it's half the original radius. However, it's moving twice as fast. It's 2v. So again, we're still solving for Fc. Mass is the same at 1. Velocity was 2, so this is 2 squared. The radius was originally 1. It's now being r divided by 2, so it's 1/2, or 0.5. So it is 2 squared. 1 times 2 squared divided by 0.5, and that is 8. So the Fc for letter D is equal to 8 newtons. The question asked us, which scenario has the least centripetal force? So letter A was 1, letter B was 4, letter C was half a Newton, and finally option D, letter D, was 8 newtons. So the least centripetal force is by option C. Okay, there you have it. I hope that this was helpful with solving some of what seem to be more complex problems, but they're pretty easy once you get the hang of them. Have a wonderful day. Take care.